Hello and welcome to lesson 52 of Additional Maths with Mr. Barrow. In this lesson, I'm going to go through questions 11 to 16 of the sample paper on OCR's website. Make sure you've tried that paper and those questions before watching this. In the previous lesson, I went through questions 1 to 10. Okay, so let's get started. Question 11. Here we have a graph of a function which is y equals the square root of 2 to the power of x. Okay. Part A says use the trapezium rule with two strips to estimate the area enclosed by the curve, the x-axis, x equals 2 and x equals 4. Okay, so let's just start defining that area that I'm trying to find. So the curve is one boundary for that area. The line, which is the x-axis, is another. So we've got the curve and the x-axis, and then the lines x equals 2 and x equals 4. So in effect, we're trying to find this green shaded area here. And we're doing so by splitting up that area into two strips. Two strips which are both trapezia. And if I find the area of the two trapezia and add them together, I will get an estimate for the area that I want to find. Okay, so the two trapezia will be the one between 2 and 3, between x equals 2 and x equals 3, and the one between x equals 3 and x equals 4. So I'll call that trapezium 1 and trapezium 2. Now, clearly, as you can see, that area under the curve will not be a trapezium because the curve is a curve and the trapezium is made of straight lines. So if I drew a straight line for the trapezium, it would be slightly above the curve. It's quite difficult to draw a straight line and show you very clearly, but the first one just slightly goes above it, and so does the second one. It's just that the curve is difficult to see underneath that line. So if I found those two trapezias area and then added them together, I would have an overestimate of the area that I actually want because the curve actually bends underneath those two straight lines. Okay, so to find the area of the trapezia, I can either use, as it says, use the trapezium rule, or I can just use common sense and try and work out the area of the two trapezia that I've indicated. Okay, which in effect would be using the trapezium rule, but just be doing it slightly differently to the formula that's given. So what we want to do is we want to find the lengths that we have, which are the parallel lines. So the length there, the length there, and the length there. So the lengths that take you from the x-axis to the curve, which are actually the y-coordinates of the points on the curve at those, for those values x equals 2, x equals 3, and x equals 4. Okay, so I'm going to do a little table for x-coordinates and y-coordinates for the values of x being 2 and 3 and 4. And I want to find the corresponding y-coordinates because those will be the parallel lines on my trapezia. Okay, the parallel lines on the trapezia, which are important because, as we all know, the area of a trapezium is half the sum of the parallel sides multiplied by the distance between them. That's how you calculate the area of a trapezium. So when x is 2, y is equal to the square root of 2 to the power of 2. So the square root of 4, which is 2. So y is 2. And as you can see on the graph, you can see a y-coordinate of 2 there. When x is 3, we have y is equal to the square root of 2 to the power of 3, so the square root of 8, which is 2 root 2, or I'll just put root 8 here and leave it in surd form rather than putting an ugly decimal there. And when x is 4, we have y equals the square root of 2 to the power of 4, which is the square root of 16, which is 4. And as you can see on the graph, we have a y-coordinate of 4 there as well. Okay, so To find the area of a trapezium, I'm going to do it common sense way first, just finding the area of the two trapezia together and then adding them up. And then I'm going to use the formula that's given and show you that either way will give you the same answer, and it's up to you to decide what to do. So either we do area of trapezium 1 that I've indicated on the graph there, which is approximately, because remember this is an estimate, half times the sum of the parallel sides. The parallel sides for trapezium 1 are 2 and root 8, multiplied by the distance between them. The distance between the trapezia is this distance between 2 and 3, which is just 1. And then the area of trapezium 2 is approximately half times the sum of the parallel sides are root 8 and 4, multiplied by the distance between them, which is 1. And then if I combine those and find the total area, it's approximately those two added together, which would become 3 plus 2 root 2. Which is also, if I put it in decimal form, 5.83 to 3 significant figures. Okay, so that's just using common sense. Now, if I was using the trapezium rule, which is given to you in the formula book, and it's given here below, it looks relatively complicated, but what it is in effect is half times h, and where h is given as b minus a over n. Now, b minus a is this final value minus the first value. So basically the distance between the last and the first value, and then divided by the number of strips you want. So 4 take away 2 is 2. So there's a distance of 2 between the limits. And then we're sharing it into 2 sections, which is 1. So h is in effect the distance between the parallel sides. So using the trapezium rule, the area is approximately half times 1 multiplied by, and then in big brackets, y0 and yn are the end y values. So here the end y values are 2 and 4. So 2 plus 4. And then added to 2 lots of any other y value we have. We only have one other y value, which is root 8. 2 lots of root 8. The reason why we're doubling root 8 is because it's used in 2 different trapezia. We use this root 8 in trapezium 1 and in trapezium 2, so it needs to be doubled. Okay, it's the only one which we use twice because we're only using 2 trapezia, so that's the end of our calculations. And if I simplify that down, that will also give me the same answer, 3 plus 2 root 2, or 5.83 to 3 significant figures. And it also asks us to state whether this is an over or underestimation. And since the trapezia, the straight lines, are above the curve goes below, then the area that I've found, which is the area of the trapezium, is an overestimate. Okay. So let's have a look at part B, part 1. So part B is talking about gradients of the curve. So it's no longer about finding the area. So I'm going to erase the work that I've done on that so far. And let's have a look more closely at the curve. Use the chord from 2,2 to 4,4. So from there to there. So if I draw a straight line between those two, that chord, use that chord to estimate the gradient of y equals the root of 2 to the power of x at x equals 3. So what it's essentially trying to do is it's trying to find an estimate for the gradient at this point. So if I drew a tangent at that point, x equals 3, that green chord is approximately going in the same direction. So it's a pretty good estimate for the gradient of the tangent at x equals 3. Okay. The problem with gradients of tangents is that we only have one coordinate. If we have a chord, we have 2 coordinates, and we can do the gradient, which is the change in y over the change in x. Okay, so we're going from 2,2 to 4,4. The change in y is 2, from 2 to 4. So we do 4 take away 2 for the change in y. And then the change in x is also 4 take away 2. So that's 2 divided by 2, which is 1. So the gradient of the chord, the green chord on my graph, is equal to 1. And that's an estimate for the gradient at x equals 3. So, part 2. Determine an estimate for the gradient of the curve at x equals 3, which is an improvement on the estimate we found in part 1. Well, to do that, we just need a chord which is closer together. So we've chosen between 2, 2 and 4, 4. We could do between x equals 2.5 and x equals 3.5. I'm going to choose to do it between x is 2.9 and x is 3.1. So really 2 points really close together. You can choose any, in the mark scheme, it'll allow anything which is closer together than these 2 points they've done in part 1. Okay, so I'm going to choose to do the point where x is 2.9. When x is 2.9, since the equation of the graph is y equals root of 2 to the power of x, then the y coordinate will be the square root of 2 to the power of 2.9. Then the other point I'm choosing is 0.1 to the right of x equals 3. So 3.1. When x is 3.1, the y coordinate would be the square root of 2 to the power of 3.1. And so I've got 2 coordinates. So the gradient of that chord will be equal to the change in y, so the root of 2 to the power of 3.1 minus the root of 2 to the power of 2.9 over the change in x, which is 3.1 take away 2.9. And that is equal to 0.980 to 3 significant figures. Okay, so that there is a better estimate for the gradient of the tangent to the curve at the point where x is 3. So let's have a look at the mark scheme. So that answer, 0.980, that gave, actually that's pretty good, because the actual answer, if you use differentiation, is 0.980 to again 3 significant figures. So my answer, which is 0.980 to 3 significant figures, is extremely close. Now, they used the trapezium rule. I showed 2 different ways to get 5.83, and there we go. If you want some more practice on this, see lesson 35 for part A, which is estimating the area under a curve using the trapezium rule. And see lesson 33 for part B in this question, which is estimating gradients of curves. Okay, let's have a look at question 12. So in question 12, we have china cups packed in boxes of 10. It is known that 1 in 8 are cracked. 1 in 8 of the china cups are cracked. Okay, so 1 in every 8 in the large selection are cracked. I mean, when you pick out 8, it doesn't mean that you are definitely going to get 1 cracked one, because you might pick out 8 which are perfectly fine and miss out the cracked ones. But overall, 1 in 8 are cracked. Find the probability that in any box of 10 chosen at random, exactly 1 cup is cracked. So this is a classic binomial distribution question where you have a certain constant probability of success being finding a cracked cup. I know that sounds bizarre, surely that's a failure, but we're talking about binomial distribution where you have a chance of success remaining constant, and you can define the success as whatever it is. I like finding cracked cups, so there we go. That's my chance of success is 1 in 8. And you have a certain number of trials. Now here, the number of trials we have is 10, because we are trying out 10 different cups and seeing whether we have any cracked ones. And X is the number of cracked cups. And X takes this following distribution, which is a binomial distribution with 10 trials and 0.125 or 1/8 as the chance of success, which is finding a cracked cup. And we want to find the probability that X takes the value 1, meaning that 1 out of the 10 are cracked. So for this, it could be the first one's cracked and then the rest are not cracked. It could be the second one is correct and the rest are not correct, etc. If I did a tree diagram, I could go correct, and then the rest being not correct, etc. And so that would be 1/8 times and then 7/8 times 7/8 times 7/8, etc. The rest of the 9 cups. Or it could be a different combination where I find the correct cup. In fact, there are 10 choose one ways of getting a correct cup from 10 cups. Basically, 10 different ways, because it could be the first cup or it could be the second cup, or third cup, etc. that I look at, which is correct. So there are 10 different possible ways of getting one correct cup from 10. And so there are 10 combinations of ways of going down the tree diagrams. In each of those ways, I'm going to multiply 1/8 by 7/8 to the power of 9, because I'm going to fail, i.e. find perfectly fine cups 9 times and get one success, i.e. one cracked cup. And if I do that, that is 0.376 to 3 significant figures. Now, part B. Find the probability that at least 2 cups are cracked. So that's the probability that x is greater than or equal to 2. Now, when you have to find multiple different possible options, you then find each individual one and add them together. So this is the probability of getting 2 cracked, plus the probability of getting 3 cracked, plus 4 cracked, 5 cracked, 6 cracked, all the way up to 10 cracked. Now, that would take me a long time to add up all of those different possible options. So you've got to be clever and think, well, what's an easier way of doing this? Well, instead of finding 2 or more, I'm going to find the opposite of that, which is 1 or fewer. So I'm going to find that, and then I'm going to take that away from 1, and that will leave me with its opposite, which is 2 or more. So 1 take away the probability that x is less than or equal to 1 will give me the answer in an easier way to find. So it's 1 take away the chance of getting either 0 cracked or 1 cracked. So I find each of those individually and add them together and then subtract that from 1. I've already found probability x is 1. It's 0.376 to 3 significant figures. The chance that I get no cracked cups is 7/8 to the power of 10, because there's only one way of doing that, and that's getting a perfectly fine cup time, and then another perfectly fine cup, etc., 10 times in a row. That's 7/8 to the power of 10. Plus our answer from previously, the answer to A. Hopefully I haven't cleared my calculator, so I can just use the answer to my previous calculation rather than having to type it out again. And if I do that correctly, I should get 1 take away 0.63889782, etc., which is, to 3 significant figures, 0.361. And there's the answer to the question. Okay, let's have a look at the mark scheme. There we go. If you want more practice on this, see my lesson 25, which is on the binomial distribution. Okay, let's have a look at question 13. Aha, 3-dimensional Pythagoras and trigonometry. So in question 13, we have here a wedge. Okay, imagine a wedge that you put on the door to stop it from opening, or stop it from shutting. So we have a triangular prism. A prism is a 3-dimensional object which has a constant cross-section. The cross-section which is constant is this triangular end which goes through the shape all the way. Okay. The rectangle ABCD is horizontal, so it's on the floor, let's say. And ABFE is a square, that's important. Okay, ABFE is a square. So this blue thing that I'm drawing is a square, which means that all 4 lengths are the same and you have 90-degree angles. Inclined at 20 degrees to the horizontal, such that E is vertically opposite above D and F is vertically above C. Okay, that seemed obvious from the diagram. The area of the square ABFE is 1600 meters squared. Okay, well that is helpful because now I know that the lengths of my square are 40 meters. Because 40 is the square root of 1600. Okay. X is a point on AB such that AX is 12 meters. So that's 12 meters. So then that therefore is 28 meters. Great. I'm finding lots of things out before even starting the question. Calculate the area of ABCD. ABCD is the rectangle on the bottom of the triangular prism. So to find the area of that rectangle, I need to know the width of the rectangle. I'll know the length, it's 40 meters. So I need to know this width from B to C or from A to D. Well, helpfully, if I draw the triangle BFC, so B is there, F is there, C is there, that's a right angle triangle. I know already that's 40 meters. I know this is 20 degrees, so this is just basic right angle trigonometry. And I can use that to find the length BC, which is the adjacent side. So let's call that, I'm not going to call that X because we've already got an X on the diagram. I'm just going to call that BC. So cos 20, because I'm dealing with the adjacent and the hypotenuse, I'm using cos 20 is equal to BC over, so the adjacent side, over 40. So 40 cos 20 is BC. So the length BC is 40 cos 20, which is 37.587 ... And I'm not going to round that because I'm using that in a further calculation because I need to use that to find the area of the square. So area of the square ABCD, sorry, the rectangle ABCD is the length, which is 40, multiplied by the width. And that gives me 1,500 meters squared to 3 significant figures. Okay. Part B. Find the angle between the lines XE and XF. So I'll draw that in green. So XE and XF. Okay, well, I'm finding this angle there. It would be useful if I had all 3 sides of that triangle because I've got one side which is 40 meters. If I had the other 2 sides, and that seems relatively easy because these are right angles because that's a square. And I have the lengths 40 and 12 and 28 and 40. So that's just Pythagoras. So let me draw out that sloped square just on flat. So if I draw that out, what I'm essentially finding is that green triangle is something like this. And I know that's 40. I know that's 40. That's 40. I know that's 12. I know that's 28. And I'm trying to find theta there. So using just basic Pythagoras, I know that the length from E to X, so let me put all the letters. So we've got F there and we've got B there. So I know the length E to X is the square root of 40 squared plus 12 squared, which is the square root of 1744. And then the length from X to F is the square root of 28 squared plus 40 squared, which is the square root of 2,384. And so now I have the 3 lengths of my triangle. I can then use the cosine rule to find the angle theta. So cos theta, b squared plus c squared minus a squared, so that's root of 1744 squared, which is 1744, plus root of 2384 squared, which is just 2384, minus 40 squared, over 2 times b times c, so that's 2 times root of 1744 times root of 2384. So the rearrangement of the cosine rule, make sure you know that rearrangement of the basic formula a squared equals b squared plus c squared minus 2bc cos a. It's useful to know the rearrangement into cos a is equal to b squared plus c squared minus a squared over 2bc, rather than having to be rearranging and spending that time on a basic rearrangement during the exam. So I find cos theta by plugging that into my calculator, and then I do the inverse of cos of that answer, and that gives me 51.7 degrees to 1 decimal place. Okay, so that is the angle between lines XE and XF. So let's have a look at the mark scheme. There we go. And if you want more practice on this, have a look at lesson 18, which is on three-dimensional trigonometry. Okay, let's have a look at question 14. An object is falling through a liquid. Aha, kinematics. Movement of objects. The distance fallen is modelled by the formula s is equal to 48t minus t cubed until it comes to rest, where s is the distance fallen in centimetres. Okay, so we're dealing with centimetres. And t is the time in seconds, measured from the point when the object entered the liquid. Okay, so we are given a formula for the displacement. In fact, for the distance fallen of the object. Part A, part 1, find the acceleration when t is 1. Okay, so I've got an equation for the distance travelled, the distance fallen. The relationship between displacement and velocity and acceleration is one which deals with calculus. So if I have displacement s, then velocity is the rate of change of displacement. Okay, so velocity is ds by dt. So if I want to go from displacement to velocity, I differentiate. If I want to go from velocity to acceleration, I differentiate again, because acceleration is the rate at which velocity is changing with respect to time. So it is dv by dt. And if I wanted to go back, I would integrate the other way. So here I have got displacement, so I'm differentiating. Okay, so firstly, I need to go from displacement to velocity. So I have s equals 48t minus t cubed. So therefore, the velocity, which is ds by dt, is 48, because 48t differentiates to just 48, minus t cubed differentiates to 3t squared, so minus 3t squared. That's the velocity, but I want the acceleration. Acceleration is the rate of change of velocity, so we have to differentiate this again. 48 differentiates to nothing. Minus 3t squared differentiates to minus 6t to the power of 1, or just minus 6t. So I want to know the acceleration when t is equal to 1. So when t is 1, the acceleration is equal to minus 6 lots of 1, so minus 6. And my units are in centimetres and seconds, so acceleration will be centimetres per second per second. So there we go. Part 2, find the time when the object comes to rest. The object will come to rest when v equals 0. Okay, so therefore I want to solve when velocity, which I already have found, when the velocity is 0. So I need to solve when 48 minus 3t squared is equal to 0. When the velocity is 0, it will be at rest. So add 3t squared to both sides, divide by 3. I then get t squared equals 16. And therefore t is either 4 or minus 4. But if you think about this, this is talking about time after the object starts falling, so time from 0 onwards. So therefore 4 is the only solution that is consistent with the question. Okay, so 4 seconds after the start, we have the object coming to rest. Okay, part 3, find the distance fallen when the object comes to rest. Well, I know that the object comes to rest when t is 4. And I want to find the distance fallen. Well, I've got an equation for that. S equals 48t minus t cubed. So when t is 4, s, which is the distance fallen, is 48 times 4 minus t cubed, so 4 cubed. and that equals 128 centimeters. So that's the distance it falls until a point it comes to rest. Part B, sketch the velocity time graph for the period of time until the object comes to rest. Okay, so I have an equation for the velocity. Here it is. So I want to sketch that v equals 48 minus 3t squared between time 0 and time 4, in effect. Okay, so velocity, time. So 48 minus 3t squared. When t is 0, velocity is 48. This is a classic negative quadratic, and it's already in completed square form in effect, and the maximum point is 48 when t is 0. So if it were a full quadratic, I would have all of this part and then this part, but I only have the right part because I only have for time above 0 and up to when it stops, which is when t is 4. Okay, so there is my graph. Okay, let's have a look at the mark scheme. Okay. So if you want more practice on this, see my lesson 46, which is on kinematics differentiation problems. Okay, let's have a look at question 15. John bought a car in January 2015 for £28,000. He investigated how the value of his car might depreciate over the years. He's got the following information from the internet. So at age 0, it's £28,000. At age 2, cars of this type generally worth £18,000, etc. John believes that the relationship between the age of the car and its value can be modeled by the equation V equals K multiplied by A to the power of T, where V is the value in pounds and T is the age in years. So some exponential model. Now, since it's decreasing between the years, then the exponential model is going to be an exponential decay model. So we're going to be multiplying by a value between each year which is less than 1, and that'll help it decay. So if let's say it drops in value by 20% every year, then we would have 0.8 as the multiple. If it was dropping by 15%, that would be 0.85 every year. Okay, so multiplying by 0.85. So I imagine that's something we need to find out. Part A, write down the value of K. Well, K is very easy to find if I have the initial conditions for the exponential model. Because, and I do have that, I know the value when t is 0. So I have V equals K times A to the power of T, and I know that when t is 0, B is 28,000. That helps me because that removes the problem of the A, not knowing the A. Because when t is 0, I have A to the power of 0, which is just equal to 1. So I have 28,000 equals K multiplied by A to the power of 0, which is just K times 1. So K is 28,000. So I now know my equation is going to be, so that's the answer to my question, but I now know my equation is going to be V equals 28,000 multiplied by some constant. Like I said, if it was 15% drop each year, it would be 0.85 to the power of the number of years. Okay. Part B, show that the equation can be rewritten in the form log V equals log K plus T log A. So, part B, if I have V equals Ka to the power of T, in order to rewrite it in log form, I just simply take logs of both sides. So log V equals log of all of K times A to the power of T. I can split up the right-hand side into two separate logs because I know one of my log laws is that log of AB equals log A plus log B. You need to know your log laws. Okay, so that's one log law which we're going to use. So the right-hand side then becomes log of k plus log of a to the power of t. The other log law I'm going to use is the fact that log of a to the power of n is the same as n lots of log a. Okay, so therefore this log a to the power of t can become t log a. So I then have log v equals log k plus t lots of log a. And look, show that it can be written like that. There we go, QED, which was what was wanted. I have done what was required. Okay. John then plots the graph of log v, log base 10 of v, which is often thought of as just log v. Okay, it's the default base because we work in our number system is based around the number 10. So the logarithm to base 10 is thought of as the basic logarithm until you get to higher levels of mathematics, and then the natural logarithm, which will come to when you do A level and etc. That becomes the basic. So John plots log v against t and obtains the following graph. The great thing about if you have an exponential model, if you use a logarithmic scale, then you can create a linear graph. So these points should follow approximately a straight line. So if I try and draw a straight line through these points, I'll try my best. Microsoft Whiteboard isn't great with, it says a little ruler there, but ruler is coming soon. Okay, go away. I'll just get my own ruler and attempt. That's not bad. So you can see it's sort of a linear function when you plot it as a logarithmic graph, a logarithmic scale. Use the graph above to estimate the value, a value for a. Okay. Now, we are going to have a closer look at this equation, log v equals log k plus t log a. This is, if this is our y-axis log v, then essentially what I've got is I'm going to put that in grade. So that there is like our y-axis. So I'm replacing log v as our replacement for y. We've got a linear graph, and linear graphs, you've probably known y equals mx plus c, where m is the gradient and c is the y-intercept. Well, here in this graph, our y is replaced with log v, and our x is replaced with t. Okay, so what's left should be the m and the c. The c is the constant, so that in effect is, I'm going to write that here underneath log k, because log k is just a specific value, it's 28,000, and log k is log of 28,000. It is just a constant. T log a, I said that t was replaced with is what we replaced the x with. So it's like I've got x there. And then log a has replaced the m in the mx plus c. So log a actually represents the gradient of this graph. And that's going to help us find the value, an estimate for the value of a. If I can find the gradient of this line that I've just drawn, I can find the value of a. Because firstly, that gives me the value of log a, and then I can use that to find the value of a. Okay, so log a is the gradient of that graph. So log a is approximately the change in y over the change in x of that graph. Now, the change in y, I'm going to take the two furthest apart points, these 2 points, when x is 0 and when x is 8. In order to find the change in y and the change in x, I need to have the y coordinate, which is log v. And I just want the y coordinate for when x is 0 and when x is 8. When v is 28,000, log v is log of 28,000. Okay, which will be some decimal value, log of 28,000. And when v is 4,700, log v will be log of 4,700. So that's what the y coordinates are, where it looks about 4.4 here. That's approximately what log of 28,000 is. And 3.6-ish is approximately what log of 4,700 is. Okay? But I'm just going to keep log of 28,000 and log of 4,700. So the change in y is log of 4,700 minus log of 28,000. Over the change in x, well, the change in x is from 8 to 0. So that's 8 take away 0, which is just 8. And that is approximately negative 0.0968 ... So that's what log a is. If that's log a, then a is therefore approximately 10 to the power of that, because log base 10 and 10 to the power of are the inverses of each other. So if I have log of a, then to find a, I put 10 to the power of that. So 10 to the power of negative 0.0968 ... gives me my value of a, which is 0.800 to 3 significant figures. Okay, so it does look like it's about a 20% drop in value every year. Okay, use this model to estimate the age of John's car when its value drops below 3,000. So now I'm going to write down the model that we've got. The model for the value is equal to 28,000 multiplied by 0.800. I'm just going to put 0.8 to the power of t. I'm just going to round it because it's a model, it's an estimate. It doesn't have to be the perfect answer. And also these values are all estimates anyway. So I want to know the value of t for which the point at which the value of the car drops to 3,000 and then goes below it. Okay, so I'm going to replace value with 3,000. And I'm going to solve this equation where 28,000 times 0.8 to the power of t equals 3,000, and I want to find the time. So divide by 28,000, we get 0.8 to the power of t equals 3,000 divided by 28,000, or 3/28. And therefore, t is log base 0.8 of 3/28, which is 10.0 to 3 significant figures. So around 10 years old is the time when the value first drops below 3,000, just after 10 years. Okay, let's have a look at the mark scheme. There we go. If you want more practice on this, lesson 30 is on reduction to linear form, the second part of that, which is very similar to these types of questions. Okay, final question, question 16. A bicycle factory produces 2 models of bicycle, A and B. Model A requires 20 hours of unskilled and 10 hours of skilled labor. Model B requires 15 hours of unskilled and 25 hours of skilled labor. The factory employs 10 unskilled and 8 skilled laborers, each of whom work a 40-hour week. So if each of them works a 40-hour week, then what I have is I have 400 hours of unskilled time available to me, and 8 lots of 40, so 320 hours of skilled time available, okay, to be used during the week. Okay, suppose the factory makes X model A and Y model B per week. Show that the restriction of unskilled labor results in the inequality 4x plus 3y is less than or equal to 80. So we're focusing on unskilled labor. Okay, so that's this part here. I know that if I made one model A bicycle, that would require 20 hours of unskilled labor and 10 hours of skilled labor. If I had 2 model A's, that would be 40 hours of unskilled, 20 hours of skilled. If I had X, because it's X model A's takes up x lots of 20, so 20x unskilled, and 10x skilled. But I'm focusing on the unskilled for the moment. Y model B's takes up 15y unskilled hours, because every model B requires 15 hours of unskilled. And so if I have y of them, that's 15y. So 20x plus 15y is the total of unskilled work needed to make this. And that has to be less than or equal to my total amount of unskilled available to me, which is 400 hours. And then that simplifies to 4x plus 3y less than or equal to 80. So that's where that comes from. Part 2, find a similar inequality from the restriction on skilled labor. Okay, so here we're talking about that part and this. So 10x and 25y has to be less than or equal to 320. 10x, 25y, less than or equal to 320, which simplifies to 2x plus 5y is less than or equal to 64. Okay, so that's my second inequality. Draw graphs for the two inequalities and shade the feasible region. Okay, now I had a look at this piece of graph paper they gave me for this sample paper, and I didn't like it, because if I use it where every little square here, every little square was 1 unit, then it wouldn't quite be enough. It would be enough to fit, but it would be sort of quite condensed, and most of my graph would be just sort of around here, and I wouldn't be reusing the majority of the graph. And if I try to use it as 2 squares for every 1, it wouldn't be big enough, this graph, quite. Okay, so I created my own graph to draw it, and I've drawn it on the right. But I'm going to first try and attempt to use it on this one, because you've probably done it yourself, and so you want to check what you've done. So we want to draw these two inequalities on our graph, and then shade the region which is left. Okay, so we have the x-axis and we have the y-axis. So I'm going to do a scale where it's like that. Actually, before I do the scale, I should explain why I'm using this scale. I'm going to be drawing 2 lines to help me do these inequalities. In order to shade an area defined by an inequality, it's going to be bounded by a straight line if it's a linear inequality. Okay, so to show the area bounded by 4x plus 3y is less than or equal to 80, I draw the line 4x plus 3y equals 80. And then I am going to be on one of all the other sides of that line for 4x plus 3y is less than or equal to 80. It's going to be a solid line because it includes, it's an inclusive inequality, it's less than or equal to. To draw 4x plus 3y equals 80, the easiest way I find of doing equations in this form rather than in the form y equals mx plus c is just finding the zeros, finding the y-intercept and the x-intercepts. Okay, so to do that, I just think, well, what's the value of y when x is 0? And similarly, what's the value of x when y is 0? So when x is 0, the 4x is going to be 0 and 3y is going to be equal to 80. And so y is 80 divided by 3, or 26 2/3. And similarly, when y is 0, 3y is 0 and 4x is equal to 80, so x would be 20. So I know I'm going to have an x-coordinate of 20, which is the x-intercept. I'm going to have a y-intercept of 26 2/3. I'm going to do similarly for my equation, which I'm going to do in green, 2x and 5y equals 64. So I'm going to draw the line 2x plus 5y equals 64, and then I'm going to decide on one side or other of the line because I need 2x plus 5y is less than or equal to 64. So my zeros, my x-intercepts and my y-intercepts. So when x is 0, 5y would equal 64. So y would be equal to 64 divided by 5, which is 12.8. And when y is 0, 5y would be 0, and therefore 2x would equal 64. So 1x would equal 32. So I know I need to go maximum 32 in the x direction and maximum 26 2/3 in the y direction. So as I said, my scale, I don't really need to go this far to 40 and beyond. But if I try to expand my scale more, this graph doesn't really allow it very well because it's not quite enough for me to do so. So let's draw the blue line first. The 4x plus 3y equals 80. So it goes from 26 2/3, which is about there, to there as the y-intercept. And I draw my straight line as best I can. Pretty terrible, but there we go. There's going to be a better one in a second. And since I want 4x plus 3y is less than or equal to 80, I think which side of the line will give me that? Which side of the line will the x-coordinate, the y-coordinate, if I times the x-coordinate by 4 and times the y-coordinate by 3, would it be less than or equal to 80? Well, it's more likely to be on this side of the line, because let's just try a point on this side of the line, like, for example, 0, 0. Does that work in that equation, in that inequality? 4 zeros plus 3 zeros, is that less than or equal to 80? Yes, it is. And therefore 0, 0 is on the correct side of the line, and therefore I want below that straight line. Now let's do the green line. So 0, 12.8 is the y-intercept, which is approximately there. And 32, 0 is the x-intercept, which is approximately there. And so I draw my straight line as best I can. It's terrible. So I try that again without letting it move so much. Again, not great, but I'll show a better one in a second. So this here, which side of the line do I want? If I want 2x plus 5y is less than or equal to 64, again, I can just choose 0, 0 to see whether does that work in that inequality, and yes, it does. And so I do want below that line. So I want below the blue line and below the green line. And so what's left is this area, this orange area here, which is my feasible region, which I'll call R. R representing the feasible region that I want. The reason why it doesn't then extend to the left of the y-axis and below the x-axis is because, well, I can't make less than 0 values model A's and less than 0 model B's, so there'll be no negative values of x and y. So it'll be just contained within the positive quadrant. Now, I drew it much nicer earlier, and that is how I got it, with a better sort of expanded scale so that it fits more nicely on my graph. Okay, so I'm going to try and move that. No, I'll just leave that there for the moment, and we'll come back to that and use that for our next part. Part C. Show that making 15 model A bicycles and 5 model B bicycles is possible. Well, A is defined by X because I make X model A's, and B is defined by Y, so therefore this is really the coordinate 15, 5. Is 15, 5 in my feasible region? So let's look at the best graph I have. 15, 5 is there, and so just by showing it on the diagram, you say, yes, yes it is. Okay, yes, in feasible region. Part D, the factory makes a profit of £40 on model A and £60 on model B. Write down the objective function. So for every model A, they get £40. So if they made 3 model A's, they would make £120. They make X model A's, so the profit on model A's is 40X. They make £60 for every model B. They make Y model B's, so that's 60Y. So the profit is equal to 40x plus 60y. P is usually used as a letter for the objective function. So here, P is equal to 40x plus 60y. That is what we're trying to maximize, what we're focusing on. Find the number of each that should be made to maximize the profit. So here we really look carefully at our feasible region. If I want to maximize the objective function, the maximum values will be somewhere near the vertices of our feasible region. There are lots of possible options. I could choose to make 0 of each. Obviously, that's not going to make me any profit. I could make 1y and no x, 2y's and no x, 3y's and no x, etc. I could make all of these coordinates are a possible option. But what I really want is to maximize the profit. So I really want quite a lot of each of x and y. So that's going to be near the extremes. So the extremes are going to be here. Let me just have a little closer look. That isn't the greatest 12.8. I've done 13.8 there. Apologies. So it should be there as the maximum. So my blue line is slightly too high, but never mind about that. I will erase that blue line and redraw it in my better graph. So 12.8 is there. So there we go. Okay, so the value of 12 in the y direction and 0 in the x direction is one possible option. It goes all the way across because 12.8 is quite high. It goes all the way across to actually 212 is still inside this objective in this feasible region. I can check that by seeing whether 212 works in the inequality 2x plus 5y is less than or equal to 64. So 212 is better than 012 and is better than 112 because I will have more profit with the point 212. So the point 212, x is 2, so that would be 2x's would be 4. Y would 12, 5y's would therefore be 60. 4 plus 60 is 64, so that is less than or equal to 64. That would be right on the line, that point 212. My sort of slightly wobbly line doesn't quite show it very easily there. So 212 is the best one near this vertex. Now let's go near this vertex here within our feasible region. So points such as 14.7, which is just in our region, and I'll show that by trying 14.7 in this coordinate. 2 14s are 28. 7 5s are 35. 48 and 35 is less than 64. It is 63. Sorry, 28 and 35 is less than 64. It's 63. So 14.7 works, as does 15.6. So 15.6 is just there. And also 20.0 is in our feasible region. So those are the points that I'm going to try. So I'm going to write those down as points that I'm going to try. So I want to find the integer coordinates near A, B, and C. Near A, that coordinate, that vertex, B, that vertex, and C, that vertex. Okay? So I want to find the value of the objective function P for each of these. So I've chosen 212, I've chosen 14.7 as another coordinate, and I've chosen 15.6 as another coordinate, and 20.0 as my final coordinate. And I want to find the value of P, the profit for each of those. If I substitute those values into this objective function, I get £800 for 212, I get £980 for 14.7, £960 for 15.6, and for 20.0, I get £800. So clearly, the one which maximizes my profit gives me £980, and that's at the point 14.7. And the question said, find the number of each that should be made to maximize the profit, and that is make 14 model A's and 7 model B's. This type of question is always very fiddly, especially when you don't have a pencil and a ruler on a computer like screen like this, but hopefully you will have better joy in the exam when you've got nice graph paper and your pencil and your ruler. Just make sure, if you can't quite see whether a point is within the feasible region, just check it against the inequality and see if it works. Okay, here's the mark scheme with their obviously perfect graph, except for they've got dotted lines, which shouldn't be. It should be solid lines on the mark scheme because the inequalities are inclusive. They include the line because it's less than or equal to. And also they didn't shade the region. They shaded what they didn't want, whereas the question said shade the region. So it should be that this area here is shaded. Okay, so if you want more practice on this specific topic, go to lesson 13, which is about linear programming, which is this topic itself. Okay, so that's the end of the specimen paper. I hope you enjoyed this video. Hope it was helpful. If you're doing the exam soon, good luck. If it's a while away and you're just enjoying doing some extra questions, well done. Good on you. Enjoy.